So we started learning about transfer learning. And to be honest, the rest of this course, most of it, is going to be about transfer learning. But these are the first few papers, at least in computer vision, that started noticing that they can use the features that a neural network learns and apply those features to new data sets or new tasks. The first paper was trying to approach it in a systematic fashion and try to explain what type of behavior we might see. The next two ones are really practical, but I'm gonna go through them really fast. And let's start with this one. You're gonna hear DeCAF a lot. Why? Because you are gonna see that it's getting cited whenever people talk about transfer learning, and I want you to be familiar with it. So DeCAF is a neural network similar to AlexNet, but that doesn't really matter. We are gonna take the last features of a convolutional neural network and use that to do new tasks and do transfer learning. So let's start with the visualization. TSNE is a visualization technique. I'm not gonna go through the details of how it works, but it's a paper written by Jeffrey Hinton. So it's not about deep learning, it's mostly about visualization. And what we are doing is visualizing the features in the first pooling layer, and that's gonna be DeCAF 1, and the second to last hidden layer, and that's gonna be DeCAF 6. And these are gonna be high dimensional features, and these points that you see are images that are being pushed through your neural network, and you're taking a look at the first pooling layer, the values of your neural network at the first pooling layer. This is gonna be high dimensional. To visualize that in 2D, you're gonna use TSNE, and that's gonna help you visualize your features, your images. You can do the same thing for deeper into the neural network near the labels. So these labels that you're seeing are the ground truth that we are using to color code. So let's see. Let's take a look at, for instance, hunting dog. And for hunting dog, for DeCAF 1, you see that these classes, or these big classes of categories, it's hard to distinguish them in this visualization. But deeper into the network, these are going to become more discriminative. So you're going to be able to discriminate a hunting dog from structure, from covering the yellow ones, from birds, from invertebrates, this blue, the light blue one. But here, all of them are getting clustered together. And each dot that you see is an observation. The color is going to be the corresponding class. Now you see these are getting more discriminated in the deeper layer. And this observation, we already saw it in previous papers also. The first few layers are going to detect edges, colors, etc. The last layers are going to learn more that there is a face of a dog. There are some discriminative features, and they are going to be more meaningful. This is another way of arriving at the same conclusion. So first layers are learning low-level features, and the later layers or the latter layers are learning semantic or high-level features in your neural network. Now, how transferable are those features? This study was being done on the same data set that the network was trained on. Now let's change the data set from ImageNet to images of indoor scenes, indoor and outdoor scenes. And you can see that these features for DeCAF 6 are still discriminative in a new data set without any training. You can see that there is outdoor man-made, the red ones, are being discriminated from outdoor natural and man-made, and these are all indoor. So outdoor and indoor are clearly separated apart from those features on a new data set without any training. So this is encouraging.
Can I ask a quick question?
Yes.
Should we attribute any importance to the spatial location of these two, like point clouds? Like I see that these outdoor, should we associate where invertebrate and bird are in the point cloud, and then look at where that would be on this next point cloud and see if there's like any connection?
So no, the location doesn't matter because these things could rotate.
Okay.
It's the relative location and the fact that there is a boundary between the two.
Okay, cool. Thank you.
But we need to take this into account that we are doing a projection in 2D, and this is high dimensional, I don't know, more than 100 dimensional and even more. And you're projecting it in 2D, and the fact that there is some discrimination going on, that's impressive. But one might say that these deep neural networks are not cheap to give you the features, and you want to use them on the fly, and then do, I don't know, a support vector machine or a logistic regression at the end. Maybe they're not cheap. The answer to that is that most of the computational cost is in the fully connected layers. That's going to take 57% of the time. So that's the computational time. Also, in terms of storage, they're going to use a lot of memory. But the thing is that we usually cut the network at this point, right after the convolution. And this DeCAF is the second to last hidden layer from the convolution, or maybe after the first fully connected one. That's going to help you come up with features that are less expensive. Now let's take the same features and apply that to different tasks. For instance, Caltech 101. 101 stands for you have only 101 categories. So what I want you guys to do is to download these data sets. They are not as big as ImageNet, and take a look at them and see why they're different from ImageNet. So you have different options. These are going to give you the features: DeCAF 5, DeCAF 6, DeCAF 7. I think 7 is right after the fully connected 7. DeCAF 6 is here, and DeCAF 5 should be here. So these are the options that you have for your features. And on those features, you can do different algorithms. You can do logistic regression with dropout, support vector machine with dropout. And these are some classical techniques of giving you features. And DeCAF 6 seems to be giving you the best features for these tasks. That's giving you the best accuracy. That one, this table, is when you have 30 data points per category. So you see that this is not a large data set. You have 101 categories, 30 data points on average per category, and that's not much for training a neural network from scratch. But what you can do is train a neural network on ImageNet, where you have massive amounts of data, and transfer the features to Caltech 101. Now here is a study of the size of the data set: 30 per category, 25 per category, 20, 15, 5, 10, and 5. And this is also another indication that support vector machine using DeCAF 6 with dropout is giving you better results compared to logistic regression. And we also saw that here. So that's a new task. You can have a domain adaptation task. Are the features, so there is a question, are the features just the various weights, convolutional channels? No. You take an image, you push it through the network, and you're going to end up with a tensor. Those are going to be the features. And those features are cut at a particular layer of the network. They are not weights. They are actually what you get out of all of those operations, out of matrix multiplication and out of nonlinearities, out of max pooling, etc.
So you said that there was an advantage to this because perhaps the full network was expensive, and doing, I don't know, SVM or doing logistic regression might be cheaper, but it seems like you still need to use the entire network to generate your features.
Yes, that's correct.
So where is the computational savings? Like, aren't the last couple layers themselves generally smaller than the big, dense, convolutional bulk of the network?
No, here is an indication that they are not. The convolution is taking 32% of the time compared to 57% of the fully connected.
So that's what that diagram. Okay, so you do save a good amount of time, and then instead of doing the fully connected classification at the end, you just pass it to something else like an SVM.
Yes, but the thing that we are seeing here, DeCAF 6, this is also to answer Surush's question, it's happening here right after the fully connected. So there is still some fully connected going on. DeCAF 5 is fully convolutional, and DeCAF 7 is here right after the fully connected.
Got it.
So there is no point in using DeCAF 7 compared to DeCAF 6 because
it's more expensive and worse.
Yes, but still, if you compare it to previous state of the art for featureizing Caltech 101, this is really impressive. And you are not doing any fine tuning on these layers on Caltech 101 anymore. You just take those features and use them.
Wait, is that number of train per category just the number of examples, like your data set?
Yes.
That's really small, right?
Yeah, that's a small data.
That's crazy.
So I want you to take a look at these data sets. From this point on in the course, so far we were only dealing with ImageNet, C5N, etc. But from now on, you're going to hear a lot about new data sets. So I want you to download them and take a look at them. Do EDA, exploratory data analysis on them. So that's really important. How about a totally different task? It's not only a different data set, but it's a different task. And what is the task? You have data collected from 3 domains. Amazon, these are product images taken from Amazon.com. You're going to have webcam and DSLR. These are images taken from products in an office environment. And you're using your webcam or your digital SLR camera. So the ones on Amazon are going to have a higher quality compared to a webcam or a camera. So what is the task? The task is you have some data set, you collected some data set on Amazon, and you want to classify images using the webcam. What are you allowed to do? You're allowed to take the features, you're allowed to train on the Amazon data set, and S here stands for source, T stands for target, S and T stands for source and target. So this is your source data set, that's your target data set, and you want to adapt the domain. What are you allowed to do in the S regime? You're only allowed to train on Amazon. So you're allowed to train your logistic regression or support vector machine on data sets collected from Amazon.com, but then you're going to use it to test on images taken from using webcam. And the features could be DeCAF 6, DeCAF 7, and SURF. SURF is not a deep learning method, but these two are coming from deep learning. And you can see a huge boost. Without any training on webcam, you have a huge boost in terms of your accuracy. If you are allowed to train on the target, of course, you're gonna increase the accuracy even more. If you're allowed to train on source and target, it's gonna increase it even further. But Amazon and webcam are 2 data sets that are really far apart from each other. DSLR and webcam are closer, and that's why they're transferring better. If you visualize, webcam is the ones that have a green box around them, and DSLR are the blue, and you're using TSNE, and now you're zooming in on your data set. You see that these features are putting scissors from these 2 data sets closer to each other, and that's why they're transferring better. They are actually able to transfer at all. You can also, we saw this subcategory data set before. It's the bird data set. And these are subcategories of birds, some special type of a bird. And you can use DeCAF 6. These are the ones that are learned from ImageNet. And then you can apply it to a totally different domain. And again, this data set is a small data set. It's not enough to train a neural network from scratch. You can go to scene recognition, use logistic regression or support vector machine on the features that you have from DeCAF 6 or DeCAF 7 and be able to increase the accuracy compared to state-of-the-art without transfer learning and without deep learning. Any questions?
I have 2 quick questions. And the first one, we might have talked about this, but the reason we're doing these support vector machines or logistic regression is just because we don't want to deal with like the training of the neural network again. We just want something that's quicker and easier.
You could actually put a small neural network at the end of DeCAF 7 and then fine tune those layers, actually train those layers. You could do that, that's fine.
Okay.
There is nothing wrong with that. But the idea is that these are features, you take them from your neural network, you fix them, and then now you can use any algorithm on top of that.
Mm-hmm. Okay. And then what is this yellow neuron slice in a computation time graph?
The yellow ones, the neurons are the activation.
Oh, okay.
ReLU activations, that's how much time they're taking.
Okay, thanks.
And the red one is pulling. Any other questions? So you're gonna hear a lot about DeCAF. You can actually use that algorithm. It's up on the web, you push your images through DeCAF, it's gonna give you a bunch of features that you can use.